this video, we will explore one of the emerging hydrodynamic techniques in electrochemistry that is based on microfluidics. The miniaturization of electronics in the last 70 years brought us mobile devices like phones and laptops. A similar approach was postulated to bring the same advantages in chemistry and biology fields. In a nutshell, a microfluidic chip is a device utilizing the minute amounts of liquids in a very well-controlled manner. Referring to the previous video, the liquid flows in the microfluidic chips are laminar. The two layers of liquids flow adjacent to each other, and the only mass transfer phenomenon that occurs is by means of diffusion. A typical microfluidic electrochemistry setup consists of a polymer slab attached to the glass slide with planar electrodes. In here, these are the working and the counter electrode. The polymer slab is placed on top of the glass slide with the electrodes forming a microfluidic channel. To make the electrochemical setup work, we need a third electrode, the reference electrode. Now, we need some inlet and outlet tubings to provide the liquids into the microfluidic channel. In order to provide any liquids inside, we need a pump. The most frequently used materials for microfluidic chips is polydimethylsiloxane, in short, PDMS. It's a biocompatible, gas-permeable, and transparent polymer that allows for simple fabrication. One needs to take two special liquids, the elastomer and the curing agent. Mix them together, degas the mix in a desiccator, pour into the mold, and cure it in the oven at 70 degrees Celsius. The mold for PDMS casting can be made through photolithography in a cleanroom environment or with a simple computer numerical control (CNC) milled piece of plastic as such. Here I have some examples of planar electrodes that can be placed on the glass slide. Those here are the gold electrodes fabricated with the use of photolithography and further metal sputtering or evaporation. Here's another example. ITO electrodes, that is, indium tin oxide electrodes. One can buy fully coated ITO plates and pattern them easily by means of selective wet etching. We will continue the plot of ITO patterning in the next video. To avoid leakage, it's best to use both the flat glass slide with electrodes and the flat PDMS. They adhere to each other very well, and one needs to either use some external force to press them together or bond them by using, for example, plasma cleaner activation. You have probably heard about the general rule. The counter electrode needs to be at least of the same size as the working electrode. This rule is very important here as well, although I recommend to use at least 10 times bigger counter electrode when it comes to its surface area. In a 3-electrode system in a beaker, the conducting paths from one electrode to another are almost unlimited. In a microfluidic system, the microfluidic channel itself limits the conducting path possibilities. To avoid issues with IR drop, I recommend placing all of the electrodes as close to each other as possible. Another thing to consider is the choice of the reference electrode. There are specialized reference electrodes commercially available. For example, this one is an AgAgCl reference electrode in a gelated 3 molar KCl in a plastic body of only 2 mm diameter that is suitable for placing directly into the microfluidic channel. Should you need a cheaper option, you can use a simple tungsten wire. Just keep in mind it is pH sensitive. Let's discuss the fluidic connections now. We need to make sure that every piece of tubing, syringe, needle or PDMS is tight and leak-proof. Leakage of the liquid obviously changes or even stops the flow in the microfluidic channel. The generated bubbles can pose another problem. If such a bubble adheres to the frit of the reference electrode, it can disconnect the reference electrode from the system and make the potentiostat apply random voltage, which in conclusion leads to the burning of the working electrodes. Commercially available microfluidic connectors can help you avoid leakage issues, but are also pretty costly. Alternatively, you can use blunt needles of a bit bigger diameter than the orifice to which it is connected. We have discussed the practical aspects of microfluidic electrochemistry. We are now ready to go to the lab and assemble our own microfluidic electrochemical device. See you in the next video!